Hello, welcome to my presentation video on photovoltaic installations part 4. In this video, I'm going to talk about PV architectures for self-consumption. This section focuses on electrical installations with local PV production operating grid connected, which is the main use of PV systems in the case of self-consumption. The integration of PV system into the electrical installation can be done through a connection to the main LV switchboard, to a distribution LV switchboard, upstream to the main LV switchboard, and to the MV system. Connection at the main LV switchboard. With this configuration, the PV installation architecture can include a single PV inverter directly connected to the main LV switchboard or a group of PV inverters. The inverters' outputs are gathered to a local generation switchboard and each in its turn feeds the main LV switchboard of the electrical installation. Another possibility is to connect each inverter individually to the main LV switchboard, but this configuration is not recommended for cost, installation complexity, and maintenance reasons. The PV inverter power range used for self-consumption in commercial and industrial buildings being typically between 20 kilowatts and 60 kilowatts. It can be considered that for installed power up to 30 kilowatts, a single inverter is used, and above this value, a group of inverters is preferred. A configuration where the PV installation is connected to the main LV switchboard is used in cases where PV system is located near the main LV switchboard. PV production is used both for self-consumption and export to the grid of the excess PV energy. PV system is associated with other local energy sources like storage or CHP, for example. A connection at the main LV switchboard allows all local production to be gathered in a single area, which facilitates the maintenance and the operation of the installation. It is ideal configuration for new electrical installation or existing ones when the main LV switchboard is easily accessible. PV production capacity is between 10% to 100% of the building installed power. For smaller scale PV installations, a connection to a closer secondary switchboard can be preferred. The PV system is connected to the closest switchboard. This configuration is preferred in the situations where PV production does not exceed the consumption downstream to the switchboard it is connected to, or the PV inverters are far from the main LV switchboard. This configuration is typically used in multi-floor buildings characterized by a PV production at rooftop area significantly lower than the building energy consumption needs, and a main LV switchboard is usually located at the ground floor. The connection to a secondary LV switchboard presents the following advantages, like the cable length between the PV system and its connection point to the electrical installation is minimized, and the installation is easier and optimized. Although this configuration presents some limitations, like more complex maintenance if the number of PV sources multiplies, When a feeder is under maintenance, all power sources potentially supplying the feeder must be isolated. When connecting PV installations to the closest switchboard, the number of connected power sources is potentially higher and much more dispersed, which makes the isolation more complex. Another limitation is limited upgradability. This configuration is much less evolutive than a connection to the main LV switchboard. An extension of the PV installation may require modifications in the existing building electrical installation. A possible configuration is to connect all PV inverters and the utility incomer to a switchboard which feeds the main LV switchboard of the electrical installation. Another alternative, especially when the utility incomer and the local sources are not in proximity, is to connect a single output of the PV system to the utility incomer before feeding the electrical installation. This connection upstream to the main LV switchboard is used in existing buildings where the PV production capacity exceeds the load consumption for which the electrical installation is sized. In this case, a connection of the PV system to a secondary or main switchboard would overload the existing electrical infrastructure and will require its modification, such as replacement of cables, switchboards, and protection equipment. Coming as a better option, a connection upstream to the main switchboard does not require any modifications of the main LV switchboard or downstream to the installation. The main advantage of this architecture is its capacity to integrate large-scale PV production without impact on the existing electrical installation infrastructure. It can be used both for self-consumption and export of PV production excess. A drawback can be the need for a dedicated additional switchboard to gather all sources, which potentially increases the cost of the system. A connection to the medium voltage side of the electrical installation is extremely rare, as the PV production and the electrical installation loads are in geographical proximity. A medium voltage connection of the local PV production will require additional cost and will be less energy efficient, except if the PV production is far from the loads and with important production capacity. Operation of electrical installation with local PV production. In no normal operating conditions, electrical installations with PV production for self-consumption are characterized by two operating modes. The electrical installation operates supplied by the grid only when there is no PV production. The PV installation may be disconnected as an option through its protective device, or the electrical installation operates supplied both by the grid and by the PV installation when there is a PV production. The output waveform of the PV inverter is synchronized with the grid voltage and frequency. This function is ensured by the PV inverter embedded control. The produced PV power goes to the loads as the electricity takes in priority the path of least resistance. Consequently, there is no need for specific equipment redirecting the flow of electrons. In case where the PV production exceeds the instantaneous consumption needs of the electrical installation, one of the following management strategies can be adopted. inject the excess power in the grid where it is consumed by other users. The injected power can be remunerated at the wholesale price of electricity or at other tariff or not given value at all depending on the agreement with the energy provider. Also, limit the PV production. Some energy providers do not allow the injection of excess PV power in the grid or authorize a restricted injection only. Use storage, another option, or share the PV excess with a community with a private electrical network if allowed by the local regulation. PV systems create some limited disturbances in the electrical installation, coming mainly from the operation of the PV inverters, and those are harmonics. As most electronic equipment, PV inverters generate harmonics. The harmonics emission is specified by the PV manufacturers. Generally, they are below 3% THDI. DC residual currents. In case of an earth fault on the DC part of the network, the feeding of a DC residual current at the AC side of the installation depends on the isolation between the DC and AC side of the PV system. Galvanic isolation between the DC and AC side of the PV installation guarantees that DC residual currents will not pass at the AC side. When there is no galvanic isolation between the DC and the AC side, the DC residual current may be present at the AC side of the installation and must be eliminated unless the PV inverter is designed to prevent, limit, or avoid such a situation. When electrical installation requires the installation of RCD of the AC circuit, the type should be selected in function of the residual current that can be present. PV inverters manufacturers usually specify the injected PV inverters maximum DC residual current and the RCD type that should be used with this inverter. In installations operating grid connected only, the PV inverters shut down automatically in the case of utility supply loss. They are not designed to provide backup power during utility outages. In the case of fault in the electrical installation, a high short circuit current flows from the utility incomer to the fault location. The PV inverters also contribute to the fault providing their maximal current, which usually does not exceed 2 times the nominal PV inverter current. Electrical faults in installation with PV systems for self-consumption are localized and isolated by overcurrent protections, and specific protection functions or devices are not required. The presence of PV inverters does not affect earth fault protection in the AC side of the installation. PV inverters and DC sides shall be protected against earth faults according to IEC 712.421.101. When operating only grid-connected, PV systems used for self-consumption are simply connected to a switchboard of the electrical installation. Loop configuration used to increase the energy availability in multi-source installations do not bring any benefit as PV inverters stop operating in case of utility supply loss. As described in the previous section, PV inverters operate in parallel with the grid. There is no transfer of operation from one source to another, thus automatic transfer switch is not required for installations operating only grid connected. As the PV system for self-consumption is part of the electrical installation, the earthing arrangement of the electrical installation applies also to the AC side of the PV inverter. If the PV inverter is with distributed neutral, this one is connected to the same earth reference as the transformer neutral. The creation of two earth references inside the same building is forbidden as currents may circulate between both earths. The earth reference remains the same as far the installation operates grid connected. Regarding the DC side of the PV inverters, there are two options: galvanic insulation between the DC and the AC side of the PV system. The earthing at the DC side does not depend on the earthing system of the AC electrical installation, or no galvanic insulation, which is in most common case. The system earthing at the DC side must be compliant with the earthing of the AC electrical installation. In case of utility supply loss, installations with local generation are required to guarantee that they do not inject power into the grid for utility workers' safety. For installations with PV production operating only grid connected, this safety feature can be met by the PV inverter. Like most PV inverters integrate anti-islanding protection, which disconnects the PV inverter in case of power outage. The presence of this protection and its standard compliance is provided by the PV manufacturer. Or a dedicated protection device installed at local sources feeders or at the utility incomer of the electrical installation. Reverse power protection for PV inverters is not required as they are unidirectional devices and do not pass reverse current. Reverse power protection may be required in the case of the presence of other local sources, such as diesel generators, where the flow of the current back to the generator may cause its failure. Reverse power protection is usually not required to prevent the power injection into the grid in normal operating conditions. This function is assured through control of local sources. Guidelines for sizing. The load flow and the short circuit current flow should be evaluated for each operating mode, and the electrical installation components and equipment should be sized accordingly, taking the worst case contrast. If storage is present in the electrical installation, it should be taken into account in the load flow and short circuit currents, calculating twice, once as a load and once as a source. In single source installations, switchboards are sized in function of the maximal current consumed by the downstream load. When a switchboard is supplied by two or more sources, it should be sized in function of the maximal current that can transit through it, which can be the current consumed by the load, the current delivered by the local sources. cable's current capacity must be higher than the maximum expected current, which should be evaluated for each operating configuration of the electrical installation. In single-source installations, transformers are sized in function of the installed load power. In installations with PV production for self-consumption, where the injection of PV production to the grid is possible, the transformer should be sized in function of the installed local source's power capacity. When a single inverter is connected to a switchboard of the electrical installation, a circuit breaker should be installed downstream to the cable connecting the PV inverter to the switchboard to isolate electrical faults or overloads occurring on the PV feeder. When several PV inverters are regrouped to a switchboard before they interface with the electrical installation, it is recommended to install protection devices at both ends of the connection between the two switchboards. The role of the downstream breaker is to isolate faults on the connection between the PV system and the building's electrical installations. Selectivity between circuit breaker 1 and circuit breaker 2 should be assured. Otherwise, a fault in the PV installation may trip the main breaker and interrupt the supply from the grid. The role of the upstream circuit breaker is to isolate electrical faults on the PV switchboard. The selectivity between the downstream and the upstream breaker on the PV feeder should be met. We come to the end of this presentation. Thanks for watching.